This lecture is a series of lectures from Section 3.5 of Math 311, a course in linear algebra at Western Illinois University. So this whole section is probably going to be one of the biggest sections in our course and probably the most important. It's going to be a little intense, so I'm trying to break this down into to a series of smaller lectures. So we'll be talking about subspaces, and then we'll see how that leads to basis, dimension, and rank. So a lot of stuff here. Let me begin. We're now going to sort of generalize when we started talking about planes and lines, and we're going to see that some of those planes and some of those lines were examples of subspaces. So I want to define what a subspace is first. Before we begin, just remember the notation. We'll be using this a lot. This little E symbol means X is an element of A. Okay, so that's what that means. So the first definition is that of a subspace, and I should have underlined this because that's what we're defining. So a subspace of Rn is a set S of vectors in Rn that meet these three properties. One, the 0 has to be an S, the 0 vector has to be an S. If U and V are elements of S, then their sum is in S. And if C is a real number and V is in S, then C times V is in S. The second condition, that's the same thing as saying that S has to be closed under vector addition. And the third property says S is closed under scalar multiplication. So, and notice that obviously a subspace, because the zero vector is in here, every subspace, no subspace is the empty set. So let's look at some examples of subspaces of R2. First of all, the zero vector, the set containing the zero vector and nothing else, that's what we call a trivial subspace, because obviously 0 plus 0 is equal to 0, and any number times the zero vector is going to be 0. So this is a subspace. Again, it's called the trivial subspace. And R2 is certainly a subspace because it certainly contains 0 and is closed under addition and scalar multiplication. More interesting example would be any line passing through the origin would be a subspace. And to give you an example here, if we take the column vector xy and where y is equal to 2x, so basically S is consists of all the ordered pairs xy that lie on the line y equals 2x. And because we can rewrite this a different way. Y is 2x, we can substitute that, so the column vectors are just x, 2x, and then we can factor out an x. This is really just x times 1, 2, vector 1, 2, and x can be any real number. So this actually turns out to be the span of the vector 1, 2. But this is actually going to be a subspace. Let's just go through the definitions. 0 is clearly in here because the 0 vector is the same thing as 0, 2 times 0, right? So that's going to be an S. If we take two arbitrary, we want to prove number 2, we need to show that two arbitrary elements in S, for any two arbitrary elements of S, their sum will be an S. So let's say if x1, y1, and x2, y2 are in S, then we want to show that their sum is in S. And in fact, it will be, because from here, this means that y1 is equal to 2x1 and y2 is equal to 2x2. So this is going to be x1 plus x2, 2x1 plus 2x2, and then we can write this as x1 plus x2, 2 times x1 plus x2. So this is an S. Okay, and then similarly, if we take a real number c times x1, y1, this is going to be cx1, cy1. This is the same thing as cx1, c2x1, which is the same thing as cx1, 2cx1. So this is an S. Okay. So we can see that this is closed under scalar multiplication, and thus S is a subspace. Okay. So those are the three things. If I ask you to prove that something's a subspace, you have to do these three things. So show that there are zeros in there, that's closed under addition, vector addition, and scalar multiplication. Some sets that are not subspaces. If we take a line that does not go through the origin, this is then this set of vectors will not be a subspace, because obviously 0, 0 is not 0, 0 is not in S. Okay, if S is this set. Let me remind you that when we put a slash through the this E symbol, that just means it is not an element of S. If we were just to restrict our values to positive values of x, or non-negative values of x, well, 0, 0 would still be in here, and this would be closed under vector addition, but it would not be closed under scalar multiplication. For example, this is S. We can see that 1, 2 is in S. But if we multiply it, let's say, by -3, that's -3, -6. Because -3 is negative, this would not be an S. Okay, so this is not a subspace either. And if we replace a linear equation with a nonlinear equation like y equals x squared, this is certainly not a subspace. I think you can come up with an example easily. Let's say a 1, 4 and 1, 1 and 2, 4. This is an S. This is an S. But 3, 5. This is not an S, since 5 is not equal to 3 squared. All right. And it turns out that the only subspaces in R2 is the lines going through the origins, as well as R2 itself and the 0 subspace. If we go up one dimension to R3, we will see that the subspaces of R3 consist of, once again, the trivial subspace, all of R3, but also the planes going through the origin and the lines going through the origin. So if we wanted to, this first example, S is corresponds to the points on the plane given by x plus 2y minus z equals 0. We can clearly see that 0 is in S, right? 0 plus 0 minus 0 is 0. If we let's take two arbitrary elements in S, if x1, y1, and z1, and x2, y2, and z2 are in S, obviously that means that x1 plus 2y1 minus z1 equals 0, and x2 plus 2y2 minus z2 equals 0. If we add these together, we get and rearrange some terms, we get x1 plus x2 plus 2 times y1 plus y2 minus z1 plus z2 equals 0, right? So the sum is an S. Okay, so this plus this equals this. That's an S. And then if we take any real number C and we multiply it by this vector, this is going to be an S because this is equal to Cx1, Cy1, Cz1, and this is an S since Cx1 minus 2Cy1 or plus 2Cy1 minus Cz1, that's equal 0, and this is true because we just multiplied this equation by C on both sides. Okay, all right. All right. So this plane is a subspace. Also, if we take a line passing through the origin, let's say it's parameterized by these equations, this will also be a subspace. If we let t equal 0, we get 0, 0, 0, and that's going to be an S. If we let x1, y1, z1 and x2, y2 and z2 be an S, then let's say x1 equals 3t1, y1 equals negative 2t1, z1 equals t1, and x2 equals 3t2, y2 equals minus 2t2, z2 equals t2. And then we can see that x1 plus x2 will be 3t1 plus 3t2, which is 3t1 plus t2. y1 plus y2 will be negative 2 t1 plus t2. And z1 plus z2 is t1 plus t2. Okay, so this will also correspond to a point on the line corresponding to t1 plus t2. So we can see that that x1 plus x2, y1 plus y2, z1 plus z2. This is an S, and also C times x1, y1, z1 will also be an S since cx1 will just be 3 ct1, cy1 will be negative 2 ct1, and cz1 equals ct1. All right, that will be a point. Okay, so this again, we're helped by the fact that this goes through this includes the origin. If it doesn't go through the origin, then we can see we're out of luck, or at least we won't have a subspace. In this example, these parametric equations once again define a perfectly good line in R3, but because V is always 1, there's no way the origin cannot be in here. So this is not a subspace. Okay, since 0, 0, 0 is not in S. Okay, and just to be clear, this one was a subspace. Okay, as was this. But this is not, and neither is the next one, because once again, this is going to be this because of this 2 here. There's no way the 0 plus 0 minus 0 is not equal to 2, so it's not a subspace since 0, 0, 0 is not in S. Now in this last example, this defines a perfectly good set of vectors, but this is not a line. We have that this is something called a twisted cubic curve, which you won't really need to know for this course. But I think you guys, obviously now, if you let t equal 0, you get 0, 0, 0. So the 0 vector will be in this, but this is not closed under vector addition or scalar multiplication. Or at least it's not closed under vector addition. And I think you can come up with an example. If you let t equal 1, you get 1, 1, 1. If you let t equals 2, you get 2, 4, 8. And if you add these together, you get 3, 5, 9. And there's no value of t for which this is equal to t squared, t cubed for any t. If 3 equals t, then 3 squared is 9. It's not equal to 5, right? So this is in S, this is in S, but this is not in S. Okay, so this is not a subspace. Okay, and you can check this would not be closed under scalar multiplication either. Okay, if you just think about it, you can come up with an example on your own. Okay. Then one thing I do want to prove is that the span of a subset of vectors is always a subspace of Rn. That is, if fv1 through vk are vectors in Rn, then the span of these vectors is a subspace of Rn. Let's just remember that the span of v1 through vk is defined to be the set of all linear combinations of these vectors. So this would consist of a1, v1, all the way up to a, k, vk, okay, such that the ai's are real numbers. Okay. So the proof of this, again, 3 things to check. The 0 vector is certainly in here because we can just choose all these a's to be 0. So the 0 vector can be written as 0 times v1 plus 0 times v2 all the way up to 0 times vk, and that will be in S. We'll just call this S again. Let's say if u and v are in S, and let's say that u is equal to a1 v1 plus if u is equal to a1 v1 plus dot 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 plus ak vk, and v is equal to b1 v1 plus dot 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 plus bk vk. Okay, for some real numbers, where all the ai's and vi's are real numbers, then u plus v, if we add these together, this will be these two together, we can, well, I'll write this out. And then we can collect the like terms, and this will be a1 plus b1, b1, all the way up to ak plus bk, bk. Okay. And this, we see this is a linear combination of the v's, so this will be an S. And similarly, if c is a real number, cu would be c times a1 v1 all the way up to ak vk. And we can write this as ca1 v1 plus dot 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 plus c ak vk. And this is another linear combination of the v's because remember c and a1, we can multiply them there. This is a real number, and c-ak is a real number, and all these other products are real numbers, right? So we'll still get a linear combination of the v's. So this will be an S, all right? So thus S is a subspace. And we'll see eventually that any subspace of Rn is actually going to be the span of a a set of vectors. Okay, and we'll also talk about how that set of vectors is not necessarily unique, and if that set is also linearly independent, that will lead us to that. We'll see that that's a basis, and but we haven't defined any of that term yet. So right now, just get a little practice determining if a set is a subspace or not, and we'll see you next time.